In this example, we have a weak acid, strong base titration, where we are asked to calculate the pH during the titration of 40 milliliters of 0.1 molar propanoic acid after adding the following volumes of 0.1 molar sodium hydroxide. Now, it's useful, before we start to solve this problem, to calculate the equivalence point of the titration. And in order to calculate this, we will simply use the equation: the concentration of acid times the volume of acid equals the concentration of base times the volume of base. And this is just a way of restating the fact that the moles of acid that we start with equals the moles of base that we add during the titration in order to reach the equivalence point. And by acid, we mean propanoic acid, and by base, we mean sodium hydroxide. So substituting the value for the concentration of the acid and the volume of the acid, and the concentration of the base, which was 0.1 molar, we can calculate the volume of base required to reach the equivalence point, which in this case was 40 milliliters, which of course is the equivalence volume, or the volume required to reach the equivalence point of the titration. So knowing the equivalence volume of 40 mils, we can now see that in this titration, with 0 mils of sodium hydroxide added, this is simply a weak acid problem. At 30 milliliters of sodium hydroxide added, this is just a buffer. And at 40 milliliters, which is the equivalence point of the titration, this is simply a weak base problem, since we've converted all of our weak acid into its conjugate base, propanoate. And at 50 milliliters of sodium hydroxide added, we have excess hydroxide, since we have passed the equivalence point. In part A, before we've added any sodium hydroxide to the system, we simply have a solution of propanoic acid, which is a weak acid. And therefore, part A is simply a weak acid equilibrium problem. So the first step is to write a balanced reaction for our weak acid, which is propanoic acid plus water as our starting point. And since it's a weak acid, we'll have an equilibrium reaction, and so we'll have the double arrow representing our equilibrium. And we know that propanoic acid will donate a proton to water, and this will produce propanoate and H3O plus as our dissociation products. So next we'll have to complete the ice table for this reaction. So we're given in the question that the initial concentration of propanoic acid was 0.1 molar. And since water is a pure solvent, we simply put a line through it because we don't consider the concentration in this case. Similarly, for the conjugate base, propanoate, we don't start with any propanoate, so we simply put a 0. And for H0 plus, we also don't start with any H0 plus, so we put a 0 for the concentration of H0 plus as well. Since this is an equilibrium reaction, we don't know the change in the concentration, so we simply use X for the change. For the reactants, the change is minus X, and for the products, the change is plus X. The next step is simply to add the columns together. So for propanoic acid, we would have an equilibrium concentration of 0.1 minus X. And for acetate, we would have 0 plus X, gives us an equilibrium concentration of X. And similarly, for H0 plus, we have an equilibrium concentration of X. And so this last line in our ice table is important because this is the concentrations that we will use to calculate the pH. The next step is to write our expression for the equilibrium constant, and since this is an acid dissociation reaction, we have Ka for dissociation constant for the acid equals the concentration of the products, which are H0 plus and propanoate, divided by the concentration of the products, which is propanoic acid. Next, we simply substitute the values in, and this gives us 1.3 times 10 to the minus 5, which is the value of Ka that was given in the question. The concentration of H3 plus is X, and the concentration of propanoate is also X. And now we divide by the concentration of propanoic acid, which is 0.1 minus X. So you'll notice that when we rearrange this equation, we will have a quadratic equation. And the best way to solve the quadratic equation is to use the quadratic formula, which is x equals minus b plus or minus b squared minus 4ac divided by 2a, where 1, the coefficient 1, which in front of the x squared is the value for a, 1.3 times 10 to the minus 5 is b, and 1.3 times 10 to the minus 6 is C. So plugging this into our calculator, we get a value of x equals 0.00113 for the value of x, which is what we get from the quadratic formula. Now, if we look on our ICE table, we see that x, if we want to calculate the pH, x represents the equilibrium concentration of H3O+. Okay? And knowing the concentration of H3O+, we can now calculate the pH. And substituting that value in for the H3O+, we get a pH of 2.943, and rounding to two significant figures, we get a pH of 2.94 as our final answer. And you'll notice that this pH is less than 7, which is the pH we would expect for a weak acid. After 30 milliliters of sodium hydroxide are added, we'll see that the sodium hydroxide begins to react with the weak acid, which is propanoic acid. Now, since the volume in the titration is constantly changing, we'll see that it is actually more convenient to do the calculations in moles, or in this case, as you'll see, millimoles. So, as you may recall, we started with a 0.1 molar solution of 40 mils of propanoic acid, and multiplying these together, we get 4 millimoles of propanoic acid. And in this point in the titration, we've added 30 mils of sodium hydroxide, and the concentration of sodium hydroxide that we started with was 0.1 molar times 30 mils gives us 3 millimoles of sodium hydroxide. So as I said, the propanoic acid reacts with the hydroxide. This is the beginning of our net ionic reaction, and this hydroxide comes from the sodium hydroxide. Here, propanoic acid, being the acid, will donate a proton to the hydroxide to produce water and propanoate, which is the conjugate base of propanoic acid. Next step in the calculation is to tabulate the initial, change, and final number of millimoles for each of the species. So the initial number of millimoles of propanoic acid is 4 millimoles, and the initial number of millimoles of hydroxide is 3 millimoles. Water is a pure liquid, so we just put a line through it, and we start with 0 millimoles of propanoate. Here we see that hydroxide is the limiting reactant. And so in this reaction, some of the propanoic acid will react with all of the hydroxide to produce propanoate. And so the change in number of millimoles is determined by the limiting reactant, which is hydroxide. And so the change is 3 millimoles. For the reactants, it'll be minus 3 millimoles for both propanoic acid and hydroxide, since they react in a 1-to-1 ratio. And for the product, propanoate, it will be plus 3 millimoles, since 1 mole of propanoic acid produces 1 mole of propanoate. The next step is simply to add up the columns, and we see that we have 1 millimole of propanoic acid. 3 minus 3 is 0 millimoles of hydroxide, which makes sense since hydroxide, as you may recall, is the limiting reactant, and 3 millimoles of propanoate, which are produced. At this point, you should be able to recognize that we have a weak acid and its conjugate base. And you can say to yourself, aha, we have a buffer. So in order to determine the pH of the buffer, all we need to do is use the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the concentration of A minus divided by the concentration of HA. Now, at this point, you might notice that we don't have the concentrations, we only have the number of millimoles. But as you may recall, the concentration is simply the number of moles divided by the volume. And since in the numerator and the denominator, the volumes are the same, and the weak acid and the conjugate base are both located in the same container, we can simply cross out the volumes, since they're the same in both the numerator and the denominator. And this leaves us with an equation that says the pH equals a pKa plus log of the number of moles of A minus, the number divided by the number of moles of HA. So the next step is to calculate the value for the pKa value, because in this question we are given the Ka for the weak acid. However, we know that we can calculate the pKa from the Ka using the equation pKa equals negative log of the Ka, and just substituting the value of the Ka into that equation gives us a pKa of 4.886. So now we can calculate the pH, which is 4.886 plus log of the number of millimoles of A minus, which is 3 millimoles of A minus, divided by the number of millimoles of HA, which is 1 millimole of HA. You'll notice that the millimoles in the numerator and denominator cancel, which gives us a pH of 5.363. And rounding to 2 sig figs, we get a pH of 5.36. When 40 milliliters of sodium hydroxide are added, we'll see that we have 0.1 moles per liter times 40 milliliters, which gives us 4 millimoles of sodium hydroxide. Now here we see that at the equivalence point, we have an equal number of millimoles of our weak acid, propanoic acid, and an equal number of millimoles of our strong base, sodium hydroxide. And since propanoic acid is a weak acid, we'll see that it reacts with hydroxide. So the reaction, just like in the previous case, was propanoic acid plus hydroxide reacts to produce water and the conjugate base, propanoate. Again, we see that the initial number of millimoles of propanoic acid stays the same, as it stays the same throughout the titration. And now we simply add the number of millimoles of hydroxide, which of course is 4 millimoles, because the hydroxide comes from the sodium hydroxide. For the initial number of millimoles of water, we said that since water is a pure solvent, we just put a line through it, and the initial number of millimoles of propanoate is 0, since we don't start with any propanoate. For the change in the number of millimoles, we see that since we have the reaction of a weak acid with a strong base, all of our weak acid, propanoic acid, will react with all of the strong base, since we have an equal number of millimoles of each. And so the change in this case will be -4 for the reactants, and looking at propanoate, we see that the change will be +4, because 1 mole of propanoic acid produces 1 mole of propanoate. For the final number of millimoles, we simply add up the columns, and we'll see that we have 0 millimoles of propanoic acid, 0 millimoles of hydroxide, and 4 millimoles of the conjugate base, propanoate. So here we see that at the equivalence point, all of the weak acid reacts with all of the strong base to produce propanoate. So everything is converted over to the conjugate base, propanoate. So at this point, we want to convert from millimoles to concentration, and we can use the formula, the concentration equals the number of moles divided by the volume, and we have 4 millimoles of propanoate, and the total volume is 80 milliliters because we started with 40 milliliters of propanoic acid, and we added 40 milliliters of sodium hydroxide, so we have a total of 40 plus 40 equals 80 milliliters. And here you'll notice that the millis cancel, leaving us with 0.05 moles per liter of conjugate base propanoate. Since propanoate is a weak base, we can write an equilibrium reaction for the reaction of propanoate with water. And since it's a weak base, we will have an equilibrium reaction, and so we'll write the double arrows. In this case, water is acting as an acid, propanoate is acting as a base, so water will donate a proton to propanoate. In that process, water will lose a hydrogen and it will lose a charge of +1, giving us hydroxide. Similarly, propanoate gains a proton, so it will gain a hydrogen and gain a charge of +1, going from -1 to 0, which gives us propanoic acid. And since this is an equilibrium reaction, we'll write an ice table for this reaction. And when we have ice tables, we should remember that we should always write the concentrations of each of the species. On the previous slide, we calculated the concentration of propanoate, which was 0.05 moles per liter. Since water is a pure liquid, we just put a line through it. For the concentration of hydroxide, on the previous slide, as you may recall, we calculated that we had 0 millimoles hydroxide, which converts to a concentration of 0 moles per liter. Similarly, we also had 0 millimoles of propanoic acid, which also converts to a concentration of 0 moles per liter. For the change in the concentration, since this is an equilibrium reaction and we don't know how much it will change, we simply put X for the change. So we have minus X for the reactants and plus X for the products. For the equilibrium concentrations, we simply add up the columns, giving us 0.05 minus X for propanoates, X for hydroxide, and X for propanoic acid. So the part of the ice table that we need to do the calculations now is the equilibrium concentrations, which we'll use to calculate the pH. The next step is to write the expression for the equilibrium constant. In this case, since this is a weak base reaction, we have Kb, which is the equilibrium constant for a weak base, equals the concentration of propanoic acid times the concentration of hydroxide, which are both the products, divided by the concentration of propanoate, which is the reactants. Substituting the values for hydroxide and propanoic acid and propanoates, and inserting the value for Kb, which is the base dissociation constant. Now in this case, we happen to have been given the Ka, so we'll have to convert from Ka to Kb using this expression. And since Kw is 1 times 10 to the minus 14, and Ka was 1.3 times 10 to the minus 5, we simply divide the two, giving us a value of 7.69 times 10 to the minus 10 for the value of Kb. And substituting all this together gives us 7.69 times 10 to the minus 10 equals X, which is the concentration of propanoic acid, X, which is the concentration of hydroxide, divided by 0.05 minus X, which is the equilibrium concentration of propanoate. Next, we can rearrange this equation to solve in terms of X, which gives us a quadratic equation, which is X squared plus 7.69 times 10 to the minus 10X minus 3.84 times 10 to the minus 11 equals 0. As you may recall, this is a quadratic equation, and the easiest way to solve this is using the quadratic formula. And substituting this into your calculator gives us a value of X equals 6.19 times 10 to the minus 6. Now, if we want to calculate the pH, we should recognize from the ice table that X is the equilibrium concentration of hydroxide, because this is the species that will help us to calculate the pH. So now that we know the hydroxide concentration, we can calculate the pOH from the hydroxide concentration, where the pOH equals the negative log of the hydroxide concentration, and substituting the value in for the concentration of hydroxide, we get a pOH of 5.207. Finally, the last step is to convert from pOH to pH, and the pH equals 14 minus the pOH, which is 14 minus 5.207, which gives us a pH of 8.792. Rounding to 2 sig figs gives us a final pH of 8.79. Just to check our results, we should remember that for a weak acid strong base titration, all of the weak acid reacts with all of the strong base and gets converted to a weak base, and therefore the pH at the equivalence point should be basic, since this is a weak base problem. When 50 milliliters of sodium hydroxide are added, we have 0.1 moles per liter times 50 milliliters, which gives us 5 millimoles of sodium hydroxide. Just as before, we see that propanoic acid reacts with hydroxide to form water and propanoates. Once again, the number of millimoles of propanoic acid always stays the same throughout the titration, and so again we have 4 millimoles of propanoic acid. For the number of millimoles of hydroxide, this time we have 5 millimoles of hydroxide, which of course comes from the sodium hydroxide. Since water is a pure liquid, we just put a line through it, and since we don't start with any propanoates at the start of the reaction, we simply have 0 millimoles of propanoate. To calculate the change in the number of millimoles, we should recognize that in this case, propanoic acid is the limiting reactant. And so we will lose all of the limiting reactant, and so the change will be -4 for the reactants and +4 for the product. And this is because from the balanced chemical reaction, we see that 1 mole of propanoic acid produces 1 mole of propanoate. To calculate the final number of millimoles, for each column, we simply add up the columns, which gives us 0 millimoles of propanoic acid, 1 millimole of hydroxide, and 4 millimoles of propanoate. Here we see that we have a mixture of a strong base and a weak base. And it can be shown that in most cases, when we have a mixture of a strong base and a weak base, the pH will be primarily determined by the amount of strong base that we have. So this is the term that we will use to calculate the pH. So in order to calculate the pH, we will need the concentration of hydroxide. And so we just have to convert the number of millimoles of hydroxide to concentration using this equation, which simply says the concentration is the number of moles divided by the volume. So since we have 1 millimole of hydroxide and we have a total of 90 milliliters of solution, we started with 40 milliliters and then we added 50 milliliters of hydroxide. This gives us a hydroxide concentration of 0.0111 moles per liter. And you'll notice that the millis cancel, leaving us with units of simply moles per liter. Now that we have the concentration of hydroxide, we can calculate the pOH. And the pOH is the negative log of the hydroxide concentration, which in this case is 0.0111 moles per liter, which gives us a pOH of 1.954. And now we can convert from pOH to pH, where the pH is 14 minus the pOH, and this gives us 14 minus 1.954, which is equal to 12.0457. Rounding, this gives us a pH of 12.05. And here we have two significant figures since we have two decimal places and the pH is a logarithm. So the last point here is to check, and at this point we should note that we would expect the pH to be basic because we have passed the equivalence point and we are in the region of excess hydroxide. In this example, a 10 milliliter sample of vinegar was titrated with a 0.5 molar solution of sodium hydroxide. In this titration, 17.5 milliliters of sodium hydroxide was required to reach the endpoint. And so we are asked to calculate the concentration of acetic acid in our unknown vinegar sample. So this is an example of a titration calculation. And the strategy for these acid-base titration calculations is simply to use the formula: the concentration of acid, Ca, times the volume of the acid, Va, equals the concentration of the base, Cb, times the volume of the base, Bb. Now this is really just a mathematical way of stating that at the endpoint, the moles of acid have to equal the number of moles of base. And by acid, we mean acetic acid. And by base, we mean sodium hydroxide. Now, looking at our question, we're told that we start with a 10 milliliter sample of vinegar. And so we should recognize that the active ingredient in vinegar is acetic acid. So this is our weak acid, and this is the volume of acid. Okay. Now that vinegar sample was titrated with 0.5 molar solution of sodium hydroxide. We know sodium hydroxide as a strong base, and so this has to be the concentration of our strong base. And we're also told that 17.5 milliliters of sodium hydroxide was required to reach the endpoint. Sodium hydroxide. Again, this is our strong base, and so 17.5 milliliters has to be our volume of base. Now we can substitute these values Oh, and we are asked to calculate the concentration of acetic acid. So here we're looking for the concentration of the acid, and that's what we have to find. So now we can simply substitute these values into our equation, and of course we're looking for the concentration of acid. We're given the volume of acid, which is 10 milliliters, and we're given the concentration of our strong base, which is 0.5 moles per liter, and we're given the volume of sodium hydroxide, which was 17.50 milliliters. So rearranging, we simply divide both sides of our equation by 10 milliliters, and that isolates our concentration of acid. We can see that the milliliters cancel, leaving us with units of moles per liter, which is the correct unit for concentration. So plugging this into our calculator gives us a concentration of 0.8750 moles per liter. Moles per liter as our final concentration. And that's the final answer.